All right, let's say we've got this quadratic function, y equals 2, x minus 1 squared minus 4. Let's say we're expected to graph this function and find the vertex, the domain, the range, the direction that it opens, so either up or down, the equation of the axis of symmetry, and the x-intercept and the y-intercept. Well, we've got a graph here, but first of all, before we get graphing it, what we should probably end up finding is what the vertex is. So remember, if we just analyze this function, we got a y equals 2 here. So it's positive. So we know that this is going to open up. We've got a positive a. The 2 is positive, so it's going to open up. And it's going to be a little bit narrower because this number is more than 1. And then the graph is going to be moved to the right 1. And then it's going to be moved down 4. So if I go to the right 1 and then down 4, this is where my vertex is going to be. So the vertex, which is normally 0, 0, this graph got moved right 1 and down 4. So the vertex is 1 minus 4, right 1, down 4. Now when we're graphing these things, since we've moved the vertex to the right 1 and down 4, then really this graph is exactly the same thing as y equals 2 x squared. It's just that we've had to move everything to the right 1 and down 4. So what I'm going to do is from this point right here, I'm going to pretend that this is my new 0, 0, and I'm just going to graph y equals 2x squared, but from this point right here. So when x is 1, if I were to go to the right 1, 1 squared is 1, 1 times 2 is 2. So when x is 1, y is 2. I put a dot there. When x is 2, 2 squared is 4, 4 times 2 is 8. So if I went to the right 2, I'd be going up 1, 2, 3, 4, 5, 6, 7, 8. And then because you know the graph is symmetrical, if you went to the right 1 and up 2, then from the vertex, if you went to the left 1, you'd go up 2. And if we go to the right 2 and go up 8, well, we must go to the left 2 and up 8. And now we can simply connect our dots. And we get the sketch of our quadratic function. So y equals 2, x minus 1 squared minus 4 would look like this. And we could label some of these points. So this is, now when we're labeling the points, of course, we're measuring from 0, 0 here. So this is 3, 4, 3, 4. This is 2, negative 2. Our vertex was 1, negative 4. This point is 0, minus 2. And this point is minus 1, 4. So here's the graph of our parabola. We got the vertex right away from the equation, and we got the direction of opening. Now it's easy to see what the equation of the axis of symmetry would be. So that's this line right down the middle here, which is x equals 1. The domain, well, for every parabola, the domain is all real numbers because it always goes to the left forever and to the right forever. The range, well, we have a minimum in this one because it's opening up. So the range would be y values greater than or equal to negative 4. Negative 4 was our minimum value here, so we have all the y values greater than or equal to negative 4. Now we've got to find the x-intercept and the y-intercept. The y-intercept's easy because one of our key points is sitting right here on the y-axis. So we can say the y-intercept is minus 2. But these x-intercepts are a little bit trickier to solve. So we'll just have to estimate them from our graph here. And again, it looks like it's at about 2.5 and maybe, so about 2.5 for this one and about minus 0.5 for the other one. Now, if we had a graphing calculator, let's get rid of these questions in here. If we had a graphing calculator, we could enter the function in the calculator. So 2 times x minus 1 squared minus 4. And I'm just going to go check my view window out. So let's go minus 3, 3. And our vertex was minus 4. So we'll go minus 4.5. But we'll go up to, let's go up to 8. And let's draw the graph. So here's a picture of the graph. Now, the graphing calculator will allow us, when we go to gsolve, it'll allow us to find roots and maximums and minimums and y-intercepts and so on. So if we want to find those x-intercepts, we could go root, hit F1, and it found that the actual x-intercept was negative 0.41. So we were fairly close in our approximation with our rough sketch there, but it's really closer to minus 0.41 when we round it to 2 decimal places. And if I hit the right arrow button, it would have been a better estimate to say 2.41 for the other x-intercept. Let's consider this example, y equals negative 1/2 x plus 2 squared. So the first thing we want to do when we're sketching the graph of this is to come up with the vertex. Well, we've got the graph moved left 2, x plus 2 is left 2, so the vertex is going to be at minus 2, and then there's nothing, the value of q at the end here is not defined, so it's like there's a plus 0 there. So the vertex will be negative 2, 0. So on my graph, here's a dot right here. We also know that this is negative, so it's going to open down. And now let's end up graphing the function. So we're going to pretend this is the new origin right here, because this is where the vertex is. And we're going to graph y equals negative 1/2 x squared, because we've moved it left 2 and up and down 0. So here's our vertex. From this point right here, we're going to graph y equals negative 1/2 x squared. So I'm going to make x 1. 1 squared is 1. 1 times negative 1/2 is negative 1/2. So when x is 1, if I were to go to the right one, my y value would be negative 1/2 right there. If I were to make x 2 into this equation, so it's like we're doing the table of values in our head here. When x is 2, 2 squared is 4. 4 times negative 1/2 would be negative 2. So when x is 2, y would be negative 2. And when x is 3, 3 squared is 9. 1/2 of 9 is 4.5 with a negative, so negative 4.5. 1, 2, 3, 4 down here. So there's a few points on the curve. And then if we've got these ones graphed, the other side's just going to be symmetrical. And so the graph of this parabola, y equals negative 1/2 x plus 2 squared, would look something like this. And now that we have the sketch, domain is always all real numbers. The range, y values less than or equal to 0, because we have a maximum value of 0 here. The axis of symmetry is the one that splits it right down the middle, and that's where x is minus 2. So x equals minus 2 is the equation of this vertical line. The x-intercept, there's only one of them, right here at minus 2. And it looks like the y-intercept is also minus 2 on this graph. And again, if we had a graphing calculator, we could enter y equals negative a half or negative 0.5, x plus 2 squared. And the view window is not great here, so I'm going to go in and change it. I'd like to go a little bit farther to the left. And instead of negative 4.5, let's go down to minus 10. And we don't need to go up to 8. We'll only go up till 2. And there we have a nice looking graph. And so if we wanted to find the roots, we can see we have an x intercept of minus 2. And if we wanted to find the vertex, well, that's our maximum point in this case. So the vertex would be minus 2, 0. And if we wanted to find the y-intercept, we could hit F4, and it would tell us that the y-intercept is here at minus 2. So the graphing technology can find these things out for us as well. Now let's say we're given the graph of the quadratic function, and we need to come up with its equation. So we know the equation of a parabola in vertex form is y equals a x minus p squared plus q, where the vertex is pq, and then a affects the shape of the graph. The vertex is very easy to find from the graph because we just got to identify what this point is here, which is negative 2, 3. So now that we have the vertex of the graph, we know that p is minus 2, so I can put in minus 2 for p, and q is 3. And then just tidying it up, x minus minus 2 is x plus 2. Oops, forgot the squared. Plus 3. So this would ensure that we have the graph moved left 2 and up 3, which is where our vertex is. So now the only thing is we need to find out what a is. Well, there's a couple ways you could do this. You could say, well, here's the vertex, and I know from the original parabola we should be going over 1 and up 1. And we should be going over 1 and up 1. And then we should be going over 2, and we should go up 4, because 2 squared is 4. So this would be the regular parabola, y equals x squared, if we started it at that vertex. But instead of going over 1 and up 1, we're going over 1 and down 2. So the fact that it's down implies that a is going to be negative. And instead of over 1 and up 1, it went over 1 and down 2. So that must mean the y values are twice as big. Or instead of over 2 and up 4, this went over 2 and down 8. So they've been doubled. So that's one way of doing it. We could compare this graph to the graph y equals x squared, of course, with the vertex in this position, and see that a would be negative 2. The other way we could do this is we could simply find another point. So this point right here is the point negative 1, comma 1. And anytime you have an equation and you're trying to find a variable, if you can put something in for the other variables, then all we would need to do is do some algebra to isolate a. So the point negative 1, 1 has an x value of minus 1, so I can put that there, and a y value of positive 1. I can put that there. So I can put the point, and I can pick any of these points on the graph, except for the vertex, into this function. And so y is 1, a we're trying to find out, x is minus 1, whoops, plus 2 squared plus 3. And now the only variable I don't know in here is a, so all I need to do is isolate that. So I'm going to minus 3 from both sides. That's negative 2 equals a times negative 1 plus 2 all squared. And negative 1 plus 2 is positive 1. And 1 squared is 1. So I've now found my a value. A is minus 2. So I can say that the equation of this graph, now that I've found A, is -2 with a vertex of x plus 2 squared and plus 3 at the end. So this would be the graph of this blue function right here. Let's consider this application of the parabola. Let's say a new suspension bridge is to be built across the river. The two supporting towers, they'll be 82 meters tall and 315 meters apart. And cables are going to be attached to the top of the towers that will support the bridge deck. At the cable's lowest point, the height of the cable is 40 meters above the water. So the question is, how high above the water will the cables be at a point 20 meters horizontally from the base of one of the towers? Is to draw a diagram. So we've got some towers here. Let's make this one of the towers. And over here we'll make this another tower. And bridge deck. And so the cables are attached here, and the cables will come down and come back up. Something like that. That look a bit like a parabola, hopefully. And down here is our water. All right. Now, we know, what do we know? We know that this distance here is 82. So is this. And we know that this distance here is 40. And we know this whole horizontal distance is 315. All the way across there. So we have to come up with an equation for this function, this parabola here. Well, if we're going to come up with an equation, we need the equation of a parabola, which we know looks like this. So we need to find a vertex and we need to find A. Now the vertex is probably easiest if we pick this point right here. So let's say this point right here is going to be our vertex, and you know what? Let's make that the point 0, 0. Because if we can make that 0, 0, then we've just found that P is 0 and Q is 0. So our equation has just become y equals ax squared. But in order to find A, we need another point on this parabola. And the only point I can see us getting that's of any use would be this point right here. So if this is 0, 0, I need to go x, this distance, which would be half of 315. So half of 315 is, let's just make sure I do this right and not make a mistake, 157.5. So my x value up here is going to be 157.5, and my y value is going to be, well, it won't be 82, because 82 is the distance from the top of the tower all the way to the bottom. So the distance from here to here would be 82 minus the 40 meters that this bridge deck is above the water, or this cable at its lowest point is above the water. So this height will be 42 meters tall. So I now have an x value and a y value. And so I can enter the y value into my equation, and I can enter the x value into my equation. And to isolate A, I'll divide everything by 157.5 squared. And I'll go to my calculator, and I shall put in 42 divided by 157.5 squared, and get a very small number for A. So when you see something like this, 1.69, and then this E minus 0.3, this is not the number 1.69. It means 1.69 times 10 to the minus 3. So let's put it in scientific notation, which means the decimal needs to go to the left 3 places. So we could write it like this if you want. 1.69 times 10 to the minus 3 would be 0.00169. So the equation is y equals 0.00169 x squared, where x is the distance left or right from the origin, and y will be the height from the origin. Okay, so now that we have an equation to model this parabola, we should be able to find the height of this cable anywhere from the origin. So let's look at what the question asks. How high above the water will the cables be at a point 20 meters horizontally from the base? So it wants to know what would this height be right here when we go 20 meters away from the tower. Well, the problem is we are measuring from 0, 0. This is our vertex here. So we need to know how far is this distance here. Well, we knew that this was 157.5 all the way over. So if we go 157.5 minus 20, then we have our x coordinate. So x would be 157.5, which is the distance all the way from the origin to the tower, but we're 20 meters away from it. So that's 137.5 for x. So now I can substitute that into there and get 0.00169 x squared. So go into the calculator. And that's good. I've already got this number in here, so I'm just going to go times 137.5 squared equals 32 meters. So y equals 32 meters. So we've just found this distance right here. And the question wants how high above the water. Well, that's where we got to add the extra 40 meters here, because that's how much the distance is below our vertex. So the total height would be the 40 meters that it takes to get to the bridge deck, plus the 32 meters that we got above the vertex of our parabola. So the height of the cables above the water would be 72 meters if we were 20 meters away from the base of one of the towers.